So in this particular session, we have a 1.5 hour long lecture. It's mostly about the 21 centimeter signal that you have already learned a lot about. I think the basics of 21 centimeter signal you have already learned, the physics of it you have already heard about. So now how you actually measure it, how you actually quantify it, that we will listen from Dr. Raghunath Ghara from ISSI Kolkata. So he'll talk about statistics of 21 centimeter signal. Yeah.
Thank you. So I'm going to discuss about the statistics using this cosmological 21 centimeter signal. Now, what was discussed yesterday is that, so there is this signal which we are looking for from the first billion years of our universe. Although this particular signal can be probed, can be used to probe as well as dark ages and post-Ilian epoch. So for this particular lecture, I will be mostly focusing on this cosmic dawn and epoch of reionization. As you know, during the dark ages, the signal is mostly like a density fluctuation dominated. It's easier to model compared to the signals which we expect from cosmic dawn and epoch of reionization. Ilian had talked about different physical processes we need to consider to model H1 21 centimeter signal, which we expect from this particular time window. And post UR epoch is, like the signal is from the galaxies in individual points, and which is like, again, easier to model. Only you need to use a bias term. Otherwise, it will follow the galaxy distribution. It's more complex to model the signal from this particular time window. Now, I will briefly discuss some of the features we expect regarding the signal from these two eras. Now, different physical processes are already discussed to you, right? You had discussed that during cosmic dawn, the first, like when the star formation has started in the universe around rate of 20 or something, maybe it can be 30, it depends on modeling, right? Here, the physical processes are heating and Lyman alpha coupling, right? So what these important quantities are for modeling this signal is this cosmology, right? That will give you a fluctuation, density fluctuation, as well as like the velocity term, which will basically is important to make a phase distortion in the signal. And there are impacts of astrophysical sources, which comes from this neutral refraction and spin temperature. Now, during this cosmic dawn era, the spin temperature fluctuation, this is the important quantity. You see, this is the CV range, and at the very beginning of star formation, signal is very weak. It is negative, somewhat here, very weak, because here, Lyman alpha coupling is not that strong. But over time, more and more source will form. So time is actually progressing in this way. More and more source form, so your Lyman alpha background, that become very strong. Your signal is still negative, but amplitude-wise is now increased. Very strong negative signal, which is absorption signal. Eventually, what will happen, there might be sources like X-ray binaries or mini quasars, which will produce X-rays, and that will start heating their surroundings. So you see these red regions, which are somewhat, let's say, 20 millikelvin in positive signal. So these regions particularly become heated, neutral, but heated. So these are emission regions. This phase transition from this absorption to emission signal happens due to heating. So in cosmic dawn, you see that nature of the signal is a combination of positive and negative signals, emission and absorption regions. Eventually, when the heating will be very efficient, your IgM, interacting medium, that will be heated. So every part of the neutral part of the universe now is emitting in positive, because heating has completed at around this particular epoch in this model. And eventually more and more galaxies will form, and that will contribute to ionization. And you see these black regions, which correspond to zero signal, is your ionized regions. And in this particular scenario, deionization will end at some point, let's say around specific 6. So this is more or less, let's say, a picture of cosmic dawn and epoch of deionization. Now, in this particular lecture, as we are going to talk about the statistics, so we need to understand the various physical processes or the signal nature from different parts of this first billion years. Hopefully, this is already clear to you. I'm repeating because a few other previous lectures have addressed this point. Now, obvious one quantity to consider is that average 21 centimeter signal as a function of redshift. So what you do, you go to a distant part of your universe. This will give a certain z, given by the distance which you are considering, and you basically angular average your chi in 21 centimeter signal. That will give you the mean at that particular redshift. If you repeat that particular exercise for different redshifts, then you will have a measurement of this global 21 centimeter signal as a function of redshift. Now, as I said that at the very beginning, this is the start of star formation in the universe. Signal is very weak due to weak Lyman alpha coupling. It starts somewhere at 0. Then it becomes negative and very strong negative. So this is the part when Lyman alpha coupling is very strong. Heating is not that efficient. Right? It becomes this very highly negative value of this differential brightness temperature average quantity. And then there is a turnover, and this is happening due to heating, X-ray heating. Okay? So eventually it will go and become positive as here heating has been completed, and it will remain positive thereafter, and eventually it will go to 0 when reionization will end. Why I'm stressing about this particular average quantity is because one type of observation is actually trying to measure this quantity. A very simple one, but it's very important one. What we can show from simulations that if you change your source parameter, or let's say we don't know the properties of the sources there during the first billion years that well, right? So if you change your source model, source properties, your expected brightness temperature change drastically. So this is good. That means like if you have a measurement that can be used to constrain your source properties, right, during this time. It depends on like the emissivity of Lyman alpha photon, X-rays, UV, as well as it depends on the cosmology. You change your cosmology, we don't know whether this is lambda cerium or whatever. If you change it, then your expected signal in average brightness temperature as a function of redshift, that will change. So using that, you can now constrain your favorite model of cosmology, as well as if you are interested, you can constrain your source model. What is interesting is that various simple-minded observations are actually trying to probe this global 21 centimeter signal as a function of redshift. Aegis, Leda, Bighorn, Taurus, Prism Mist, Reach, Sci-High are a few examples of those. So what they will basically measure is that the type of such a profile as a function of redshift. And what is at the current state, the status is that various reionization scenarios are actually ruled out by measurements of some of these observations. Among those, Aegis, Taurus are some of those observations which are able to rule out, let's say, these models which are highlighted here. This is what I am talking about, Aegis high band data, not the low band, which had the controversy, if you know. Using this high band data itself, one can also constrain cosmological models. For example, what I am showing here is that this high band data, which is not a detection, it's a measurement. Even using that measurement, one can show that a peculiar type of dark matter model, for example, fuzzy dark matter model, which has a very sharp suppression of small scale power spectra. To start with, those type of model can be ruled out. We see the importance of these very simple statistics that even like you can now constrain your cosmology. Many of you are probably aware about this edges observation driven by MIT and Arizona State University at this frequency band of 50 to 200. This observation was done in Western Australia, and what the claim was in the form of Nature paper that they have detected the brightness temperature profile around redshift 17 or so. Now, this is the profile what they presented. It's very different than what we expected theoretically. We somewhat expect that, okay, this maximum amplitude of the signal could be, let's say, around 1.15 or 0.2 in Kelvin. But what they measure that, okay, this is much, much deeper, as well as there is a quite flat bottom, which is very hard to understand from traditional cosmological model. Now, if this is true, then this particular thing has the potential that all our known cosmological view have to be changed. So this is that powerful. Still, this particular result is debated, so I'm not going to like explain what what this means and how we can explain this one. But still, the point is that even this simple statistics of 21 centimeter signal, this is so powerful that this can change the view of our cosmology. Now, let's move to other type of statistics, which is related to complex observations. Now, these are radio interferometers. Here I am listing few of them. What these radio interferometers are is actually combinations of many radio antennas located at ground at different places. What they do, they basically take the measurements of individual antennas and combine them. Using that, they are able to probe the fluctuations of this signal, which in global measurement they can't. And now we have switched our gear that now we are talking about fluctuations. For example, like this loafer, they can in principle, let's say, make an image of this signal at certain redshifts. In that way, like, okay, they can now probe the fluctuations which global 21 centimeter signal observations can't. Now, here, the simplest statistics what one can consider is, let's say, the PDA, probability density distribution of the signal. You basically take one part of your signal, you say box, cube, let's say, and you know like the signal is now, it's varying, it's a function of your positions. And you just distribute that signal in terms of amplitude. Very simple statistics. What we can expect that this PDF, it is very much, it vary if you change the redshift or state of your interactive medium and emission in 21 centimeter signal, as well as it is highly dependent on the source model what we use. At the same time that you see that the nature of this distribution, it varied drastically. It's not a Gaussian type of distribution, which also show that the signal which we are interested is highly non-Gaussian in nature. Second, another statistics, what simple statistics, one point statistics, what one can consider is variance. Very simple. Now you have information about the distribution of the signal, and you just calculate the variance. Of course, when we calculate the variance as for let's say some map, for example, let's say here, the calculation depends on the scale what we are considering, or let's say the resolution. It can change a little bit, but overall nature of, let's say, the evolution of variance as a function of redshift for a epoch of degeneration type of signal, which assume that the spin temperature is much, much larger than CMB temperature, that shows a very unique feature. For example, starting from high redshift and going to low redshift, it has started from some value, it has increased a little bit, then it got a little bit, value becomes smaller, and then it rise and then sharply drop. So all these features actually are associated to some physical processes. It's not very random. Whatever radiation model you consider, it will show similar feature. The amplitude or where its dip is happening, this can vary, but overall this feature will be unique for all radiation models. So the thing is that at this part, it is like when ionization fluctuation is dominating, the middle of ionization, let's say. Eventually, when ionization will complete, then it will drop, as there is no signal, right, at the end of ionization. And in this middle deep part, it is the part where small ionized region has started to form in the universe, which make the density field and ionization and neutral field, that correlation negative. So this is the reason why there is dip. And previously, there will be a density-dominated signal. So this is the nature. So this variance, which is calculated, this, as I said, this is dependent on the scale. So somewhat like this is associated with R spectrum at certain K value. Now, there are other one-point statistics one can consider. These are skewness and kurtosis. Now, as you know, like this variance is like, okay, power 2, but skewness and kurtosis are now, this depends on power of 3 and 4. Both of these quantities are basically showing how the field which we are considering, how this is deviated from Gaussian field or something like that. For a Gaussian type of distribution, you expect the skewness to be 0, kurtosis to be 3, while the cosmic dot start from here and going in this way, you see that it's highly deviated from 0 value, the skewness. And kurtosis is also highly deviated from 3. So the field which we are considering is highly non-Gaussian. Simple statistics, even here, if you change your source model, these curves will change drastically. Very simple statistics, but still highlighting the source properties, etc., etc. Only the thing is that 21 centimeter measurements using radio interferometer, they don't target these quantities because this will be dominated by noise. So they go for some other statistics, which we'll talk in a little bit more detail. But these are like statistics one can explore using theoretical model. Even like radio interferometers, they can, in principle, I mean, try to measure these quantities, but that will take more integration times, things like that. Right. So the radio interferometers, what quantity they are targeting is something known as spherically average power spectrum, which is dependent on the Fourier modes of the signal. You have a little bit idea about the distribution of signal in space, right, in sky. You do a Fourier transform of that particular real space distribution of your signal, and then you basically average these different Fourier components, multiplication of two quantities, in different K bins, that will give you the power spectrum, spherically average power spectrum, PK. This is one quantity radio interferometers target. Actually, to correctly say that they target a quantity named as dimensionless spherically average power spectrum, which depends on this PK, and they have multiplied K cube divided by 2 pi square. Now, the thing is, depending on your distribution of signal, the dimensional power spectrum and the K dependence looks very different. As I said, that radio interferometer observations are targeting this quantity as a function of K scales. So this is one quantity is highly used for theoretical studies. Because what theoretical studies want to do that, okay, we explore models and then we use observations to constant something. Constant our model, that model might be, let's say, constraining your cosmology or constraining your source parameter or something. So that's why like, this particular statistical quantity is highly used. For example, like if you consider, for example, like quasar contributions, if you in your simulation model there are contributions from quasars, if there are contributions from extra-socialized high mass X-ray binaries, the nature of the signals changes drastically. Also, like late reionization, effect of optical lasers. I mean, many studies actually happens, and one very commonly used quantity is this delta square spherically average path spectrum. Now, as I said, observations are targeting. There is no detection, no claim detection as well. What interferometric observation has shown till now are upper limits. So here you see that there are lots of points, and these points are from different observations. For example, like here, these 3 points are low-far observation. This is Hera observation, which is the strongest. These are upper limits, mean what the observations claim is that the power spectrum of 21 centimeter signal will be somewhat below this number. It could be here, it will be somewhere, we don't know. But only we can say that, okay, it will be below this value at certain K. Is, let's say, this one at this redshift. So with different observation probe, different redshifts, and this is more or less the summary of the status of radio interferometer observations in terms of epoch of reionization and cosmic dawn. You see that theoretical predictions of this signal in power spectrum is somewhat like this. It depends on like what type of model you consider. But still, like, okay, there are several orders of magnitude. We have to basically drag these points below to reach our expected signal level. So what can be done? So only one way to approach is that you basically integrate more observation hours into the data analysis. And if all other analysis techniques, which some of will be discussed later in this week, are correct, then these upper limits will eventually go down and touch this signal level somewhere. Even after that, if you increase your observation hour, that particular number will not come down. So that's why we will say that, okay, now we are reaching a detection. So that particular point, you can make your, anyway, different inference or this type of study to show or highlight the dependence of how this actually upper limits look like. I'm showing this very recent paper from Martins et al. This is a low power upper limit using 10 nights of observation. And the K dependence of this upper limit, you can see that these are like the new upper limits. At small scale, anyway, the upper limits are going high. So what we need to actually target is modeling, let's say, a large scale power spectrum. In your model, if you are able to include these dimensionless power spectrum calculations at small K value, that is large scale, then you will be able to use your simulation for inference. Anyway, the small scale power spectrum are quite high in amplitude, is not that useful, but these will be very much useful. And what we'll do later today is we'll use such a upper limit for our inference. We'll try to see whether we can get some information about our source model or source properties using such a upper limit observation, which is very recent. Right. So what we expect from that exercise, which we will do in the afternoon session, is somewhat like this. So different inference particular exercise has already done using whatever upper limits we have, and this is one of them. So in the afternoon exercise, we will try to reproduce this plot, for example. So I'm not going to highlight this anymore here. So till now, let's recap. What I have talked is very simple statistical quantities. I have talked about this global signal. I've talked about one-point statistics, variance, skewness, kurtosis. And I have talked about dimensionless power spectrum of the signal at various different epochs. And you understand that physical process during cosmic dawn and epoch of reionization, they drastically change the nature of the signal. So here, I will ask whether if you have any question, then ask me now. I will try to clarify before going to the next part. Any questions?
When you showed the effect of this distribution function, the 1-point statistics, the initial slide. This one, next one, yeah. So why the RSD effects are much higher in higher redshift and not much in lower redshift?
At lower redshift, so there are anyways a density dominated thing happening. So higher redshift now, RSD, so this contrast of the signal is actually quite high. You know, it's a positive emission part and negative the absorption part. If something is flowing, that will change the particular values drastically, which is not the case of epoch of reionization. So that's why, like, okay, you expect a drastic change during cosmic dawn. Okay. Anything else?
I think where you have real state next. What is this redshift space? Real space is observer and redshifted.
Right. So I think, okay, this particular concept is actually simulation related, but I will just try to briefly mention this one. So what we tried to model is this differential brightness temperature. This depends on various quantities. These are like a neutral fraction, TS, something like related to, let's say, how much radiation has been emitted from the sources. This is also dependent on this velocity term. So what is happening is that if you consider a part of your sky here, there is hydrogen which is emitting this radiation, but that hydrogen particular has also a velocity term, right? Line of sight. So even like the rest frequency of that hydrogen is 1420, as it is moving along our line of sight, it can change. So apparent position now can be different than a real position in the sky. So real position is what we, let's say, we get from simulation. We know that, okay, this particular atom is sitting here. But from observation, we don't track that one. We track the apparent one, including the redshift effect, or due to velocity, right? This is the redshift space signal, which might be slightly different. It depends on like how much line of sight velocity that particular atom is, something like that.
So it's like observer frame and
So observer
real frame.
Yeah. Anything else? Okay, then I will go forward to the next part. Now, we have talked about 1D power spectrum, spherically average power spectrum. Now, if we switch to another type of statistics, still we stay on power spectrum, this could be a 2D power spectrum. What we do is basically, if z-axis is your line of sight, then you basically if the kth component along that axis, line of sight axis, and you determine this k perpendicular, which depends on the k components in other two axes. And you, as you have done a 3D Fourier transform, you have all the information. You have information about the kx, ky, kz of a certain location. And you also know the pk as a function of kx, ky, kz. And from there, you can now produce a 2D version of the power spectrum, which somewhat looks like this. This is the power spectrum which I talked about. This is the spherically average power spectrum, right? And same of this power spectrum basically are shown in this K parallel and K perpendicular space in 2D. Now, why I'm showing this? Because now this particular power spectrum is showing much more feature compared to this 1D one. In 1D, like we have basically compress all this information and basically destroy much of it, the information term, and produce a 1D version of it. These particular features, a different combination of K parallel, K perpendicular, are now showing that this 2D power spectrum is much more powerful than the 1D one. It contains much more information, right, feature-wise. So if you use this 2D power spectrum in, for example, inference type of work, where you try to, let's say, put constant on various of your source models, like how much UV photons has been emitted, how much X-ray photons has been emitted, what is the Lyman alpha flux, how many sources has contributed to the emissions of photons, etc. Then you see that using 2D power spectrum actually works much, much better. It constrains your power parameter space. Very, very good. Now, there is another statistics named as MAPS, multi-frequency angular power spectrum. So why this particular statistics? So one thing we also need to understand when I am talking about this signal, as you can notice that signal is actually changing when you basically consider different redshifts. So there is a redshift evolution of the signal. From simulation, what we do is that we assume that each part of your simulation box is corresponding to same redshift, which we named as coeval cube. So when we try to simulate this 21 centimeter signal, you will get statistically similar type of property at every part of your simulation box. This is not a real picture when you go and try to mimic that for the observations. Observation, one axis is your redshift axis. Here you will find that there is an evolution of your signal. For example, this particular image, consider that each part of our simulation box has same redshifts. But here, when we include the redshift evolution of the signal, then this particular end of this box become higher redshift, and this become lower redshift. And that is why you see that this particular bubble has become now smaller, while this bubble has grown in size, which we expect, right? That should be the case. From observation, we basically, let's say, if this is, let's say, redshift 8, then this particular central size will be, let's say, redshift 8, and this might be redshift 9, and this might be redshift 7. So there is evolution, and this is what, from observation, we expect the signal to be. It is varying along one side, and that will be our line of sight. Along the angular direction, signals are similar. But when we are seeing that signal from observation along the line of sight, that will vary. Now, the problem is that when we go and try to estimate power spectrum, then we have to do Fourier transform. A Fourier transform assume that, okay, that particular distribution of field, that is periodic. This is not happening here. Anyway, we use that concept of Fourier transform, and we, by force, do estimate the power spectrum. But in reality, there we have to keep in mind that there is one axis where the signal is not actually periodic. So MAPS actually it includes this particular fact that it is not periodic in one direction, and try to estimate a quantity which is shown in this particular equation. What it does, it basically take different frequency channels, means different two redshifts, redshift Z1 and Z2, which correspond to different observation frequency, nu and nu2. U is somewhat, it is K, it's somewhat related to K, let's say. And it basically try to correlate the signal between these two frequency channels or two redshifts. So there is now much more information in this CL nu1, nu2, because now what we are seeing is that, okay, it's a more or less correlation between two states of our ionization, which previously was not happening. We basically were considering at a particular redshift. Now we are basically seeing that, oh, there is a redshift evolution, how rapid that is, etc. So a lot more information if we compare this quantity and the power spectrum. This is, one can in principle plot a 2D version of this one. And you see all these features, although we don't understand what different features, how to interpret those, but there are lots more information. The central slice, this is more or less the power spectrum. The nature, the diagonal particular, the evolution, this is how the power spectrum should evolve. But apart from that, this statistics has a lot more information from the off-diagonal term. And it has been shown that using map statistics also, you can constrain your parameter space much, much better compared to when you only do using 1D power spectrum. Now, if we go beyond power spectrum, right, as we have already seen that the signal which we are considering here is highly non-Gaussian. We have seen in the form of the skewness and kurtosis. And there are other statistics which actually try to quantify them. The one problem with this power spectrum, at least this spherically average power spectrum, is that this doesn't include any non-Gaussianity in the statistics by definition. So here, for example, what has been shown is that we take somewhat, let's say, a power spectrum of this nature, one from the simulation, this type, and this is from a Gaussian distribution only. Same power spectrum, very, very different maps. Now, from power spectrum, you will not be able to distinguish which is the real fit. This is a confusion now. So we have to go for other type of statistics. Now, again, I am trying to highlight here is that this epoch of ionization signals, for example, the distributions of ionized regions, etc., is highly non-Gaussian, and there are now statistics like bispectrum, which tries to quantify that. Now, in bispectrum, what we do is that, as I said, when you had done your Fourier transform, then you know each position, the kx, ky, and kz, the k vector. And you try to find combination, try to find 3 vectors, which basically satisfy this condition. K1 plus K2 plus K3 is 0. And you define a bispectrum using these Fourier components of those points. This particular statistics also is hugely used because, as you see, this is very powerful. It can distinguish scenarios like this, which power spectrum can't. Although detecting this bispectrum using 21 centimeter interferometric observation is challenging, but still, like after we, let's say, some day when this power spectrum has been detected, these will be the statistics which people will try to detect. Right. So for these statistics, now we have to some way. The problem is like, okay, you will find so many k vectors, and it's very difficult to know which combination to use, etc., etc. So first of all, we have to some way find a proper way to explore the bispectrum. As this is now become for 1D power spectrum, we have only 1 k. This is very easy. So you could basically bin your k range, and you basically average all your k modes in that k bin. It's a very simple statistics in that sense. Maps and 2D power spectrum are still manageable, but bispectrum now, as we are basically considering 3 vectors, is become too much complicated. So that's why, first of all, we have to come up with a prescription that if we want to explore different combinations of these, what will be our possible ways to do it? One possible way is to parameterize these k modes in a way that we assume, let's say, k1 greater than k2 greater than equal to k3 in this way, and we parameterize all different combinations using this theta and ratio of k2 and k1. It has been shown that, okay, if you basically explore this parameter space, then okay, majority of your combinations are done. So depending on the choice of your parameter values in the form of k2 and k1 and cos theta, there are names of bispectrum, for example, squeezed, equilateral, this type of thing. The main point from this statistics is when you explore your signal, distribution of the signal, using in this parametric form, you see that different particular epochs, for example, these are showing the neutral fractions. Neutral fractions are increasing in this way. And you see that there are features at different parts of your parameter space. So the idea is that if you use this type of features from bispectrum, then it will first of all if you are trying to use this as an inference, and you will, effectively shrink your parameter space, as well as it is showing that okay, how much non-Gaussian is present here. So Suman is one of the experts. If you want to, and there are like various of his students are actually doing this type of research. If you want to explore this particular thing, I will recommend catch them and just don't let them go. So let us switch a bit and try to discuss little bit different techniques which we can be done using this 21 centimeter signal. So there is this match filtering technique, which is visibility based. Now, visibility is a quantity that is measured from radio interferometers, right? This is a recorded version. And using this visibility, one can come up with a likelihood for a set of parameters. Now, these parameters are filter parameters. For example, this mu, this can be, let's say, if you imagine that you are using a spherical filter, simple, which is depending on a radial value, how big your filter you are considering. And let's say you also assume that this is not a binary field, this is some amplitude, the amplitude within this filter, what you are considering. Something like that. So these are like the parameters. And now you can define a log likelihood using the visibility. So these are like the observed quantity from radio interferometers. And this SF is your filter. So you have a filter and you get a Fourier transform of this. This SF star is basically is that one. And for that, what it shows that if you apply this filter, for example, around this point, your log likelihood will be maximum when it actually your filter size matches with the size of ionized regions. If you take a smaller filter, you will get a likelihood. This will not be maximum. So now what you can do, you can actually explore a parameter space. And now, so this is the map which we are seeing from our presentation. But from reality, like what we have is a visibility. Of course, we cannot make such an image. The visibility, noise dominated visibility. If you try to make an image of that visibility, what you will find is noise, not like a picture like this. But even on this noisy data, if you apply a statistics like this, you will find that it will get a posterior distribution or something like this, which match very well with the size of your ionized region. So it is showing that now we have a technique using the visibility, we can do an imaging with that visibility. Let's say if you take 20 hours of SK observation, it's a noisy data. If you try to make an image, you will not see anything, any structure. Then you go and apply this type of techniques. You'll find that, okay, best fit values for these parameters, which will give you some idea that at that noisy map, at which part there is a large ionized region. So this is good because, let's say, from a very shallow type of observation, we will have some detection of ionized region, and actually this is the indirect detection of the signal. So not direct one, but an indirect detection. So this is also a very powerful method because nowadays, as there are other observations, for example, from HST, from ZWST, we are now having a more or less many distributions of galaxies. So we might have a good understanding that, okay, around a galaxy cluster, there might be a very big ionized region. So you start looking for your large ionized region around that. This will give us more, let's say, chance to detect the signal in terms of indirect detection in this particular observation framework. Now, there are also approaches like cross correlation between different probes. One is this, of course, like we are talking about H121 centimeter signal. These are the distributions. So what make this particular distribution of signal is the sources. At cosmic dawn, these are the X-ray sources, which basically generate the contrast between the signal, positive and negative. And during the epoch of radiation, these are ionized photons emitted from the galaxies. Now, what is the power of this particular time is that we are having a lot of information about the source position from different near infrared or UV type of observations. And now we know the locations of the galaxies. If you now probe that, let's say 7, then you know the locations of these galaxies. And from H121 centimeter, this might be a noisy map. If you try to now cross-correlate between this map and the positions of these galaxies, it will give us very unique information. Why this is interesting? Because you will learn from few lectures later this week is that detecting the 21 centimeter signal is a pain. It has so much systematics, etc., to deal with. When you try to cross-correlate between two different particular approaches, you will have some benefits by avoiding systematics. So still, like there is no like detection from this approach. Only there are several theoretical studies, but this is one of the statistics one can consider. Similarly, there are cross-correlation between this H121 centimeter signal and other line intensity mapping, for example, C2. Here what we are showing, a figure from Chandrasekhar Murmu, is a light cone from recipe 6 to 7.2, and you see that this is the H121 centimeter signal, and this is in C2. See now so C2 is particularly, these are highlighting the locations of galaxies. So those will be only located around the galaxies, but hydrogen, that will be far away from the galaxies because galaxies has ionized their surrounding. So if you try to cross-correlate them, you will get an anti-correlation. And again, using this particular cross-correlation coefficient, one can show that, okay, the nature of the cross-correlation coefficients, first of all, is highly dependent on what type of radiation models you are using. And also it has been shown that using the cross-correlation, you can actually consider much better your parameter space. So I will stop here at this point, and I will try, if you have any question, then we will try to clarify before moving to the third and final round of our lecture series. Yes.
How you are defining the log likelihood? Like it is not Gaussian. Yes.
This one is, yes. So this particular approach is actually taken from gravitational wave type of approach, where your basically signal is whatever is measured is dominated by noise, and you are applying different filters. Log likelihood, so this actually depends on a type of estimator. Now you can actually define your estimator in different ways, not like it has to be a particular form. And yeah.
So it is model dependent.
It is model dependent. Your likelihood will be model dependent.
Thank you.
You can change your, for example, filter. I was talking about a spherical filter. Let's say for this figure, you try to detect this region. We don't have any information here, like we are using a spherical thing. Let's say as we don't have any information, and if you want to generalize your filter, and you probably would go for an ellipsoidal type of filter. Now your parameter space will increase, but that will give you more flexibility. And in that sense, your signal to noise ratio will be actually much larger compared to a spherical filter. The idea is like, okay, some way you have to mimic the signal around that point. If you can have a, let's say, total information about the distribution, then you use that particular thing as a filter. We don't have. That's why we started with a very simple-minded shapes.
In case of any general shape, so what is the approach like? Then
So in general, now you have to define your filter in a way. So general sense, like, is very difficult. So you start with the spherical one, which is the simplest one. Then okay, second approach will be, let's say, the spheroidal. Now you are improving a little bit. In spheroidal, you can vary 3 coordinates independently, A and B and C. That will be another level of, let's say, improvement. Otherwise, like, yeah, I mean, coming up with shapes, general shapes, I don't think there are any such very easy way to come up with a parametric form of a very general type of shape.
Okay, thanks.
Anything else? Our people are hungry already.
No, I think, may I add something?
Yes, yes.
So essentially the idea is very simple, right? So you are targeting the large ionized regions here because your hope is you will win the SNR game if you target a larger region, because then it gives you the biggest contrast. So that is number one. Then, as Raghu said, you hope that you will get a whatever idea you have from the physics, etc. Very little idea actually. You will get the approximate shape right for your filter. So you will get a good match. So now, what are the basic parameters of any ionized region? It needs to have a location. It needs to have a size, and it might have a shape. So the location may be correlated with the shape as well. So now your shape parameter can be as complex as you can imagine. So you can play, means there can be a number of parameters, but then your random walk will be very complicated, very time consuming, right?
Yes, if number of parameter increase, then the Bayesian type of analysis this will be.
So then this exercise will be extremely hard.
Right. Then start discussing the final sections of this particular session is on image-based statistics. What previously we were talking about, let's say we did a Fourier transform of our signal and we are doing various statistics. Now, why not we try to use the images? So for example, what we are claiming is that, okay, SK will detect the signal in images very quickly, etc., etc. So if that is the case, then we will have information, much more information from the images. Why not? We can, if let's say we are able to detect the signal in this way, this is a map, let's say we are able to detect, and you directly see that how the hydrogens are distributed here. We don't have to, because when you are doing statistics, anyway, you are losing much information in Fourier domain because you have simplified your picture. If you try to use these maps directly and try to get information, for example, how many big ionized regions are here, how many small, what are their distributions, morphologically, how complex those are, things like that. Very clearly, like what you can see, these are not spherical regions. Once overlap is happening, then it's a very complicated structure. And studies shows like after this reionization has like 10%, only like level of 10%, then you will find that it is percolated, means like you will find a path which, let's say, enter from this end of this room, it will go through a very tunnel type of structure, very complicated way, but it will find a way out in the other direction. So you will find a very large region, a tunnel type of structure-wise. So now you will realize that morphology of this reionization is very complex. You can actually study those using images, which we were not able to do that when we were doing this statistics in terms of K. What I want to highlight is that now we can probe various properties of interactive medium using the direct images. So morphology is very complex morphology, and there are different techniques which we can use to directly probe the morphology of the signal and quantify what actually are the different sizes or size distributions of a type of signal which we are interested. That could be emission regions during epoch of reionization, or ionized region during the, emission region during the cosmic dawn, and epoch reionization, this will be the ionized region. Here, for example, I'm showing the cosmic dawn signal. So this is the gas temperature distributions. So cosmic dawn is actually progressing in this way. Interactive medium is becoming hotter. More and more regions are becoming now have temperature around 10 to what 3 Kelvin or something like that. In such a scenario, now you see that these regions in red, which are emission regions, positive signal during cosmic dawn, right? Their numbers has increased, sizes have increased, and eventually there will be only few absorption regions left. Otherwise, the interactive medium has become heated. So now, what we can do, we can, for example, make a binary field out of these images. So these white regions are emission regions, which are now increasing in size when we are going from beginning of cosmic dawn to end of cosmic dawn. This signal, this nature particularly, let's say the binary field evolution, is very similar if you consider ionized regions and how those are growing during epoch of reionization. Okay, now you see that this is, of course, a 2D version of it. And as I said, like the morphology-wise, is a very complex type of tunnel type of structure. It's not easy to quantify, but there are methods which can be used to at least get some idea about the distributions. For example, there are methods which you use Sargent type of code, which is highly used by Choudhury and their collaborators, which basically quantify the volume of the largest structure in your particular simulation box, let's say. For this case, it is the emission region, and you see that cosmic dawn is actually progressing in this way, and this was growing slowly, and suddenly it get very much rapid increase. So this is the state where, as I said, this percolation type of thing happens. Suddenly, like all these individual emission regions, they got connected, and a huge volume of the simulation box or the universe become connected. So in this particular scenario, I mean, this is one of the visual, what you can imagine, is very repeatable for ionized region case as well. Reionization was happening, so there was individual ionized regions which were growing around individual galaxies, and suddenly many of those individual ionized regions get connected and create a very much tunnel type of structure throughout your simulation box. So that's why this rapid increase of the largest structure volume happens. This is the state known as percolation transition. So it has been shown that, okay, this percolation transition is also very much model dependent, what type of, how many sources has contributed to reionization or cosmic dawn X-ray emissions will determine like how sharp this thing will be, etc., etc. And sometimes it has shown that, okay, these largest cluster statistics are actually very much useful to distinguish fundamental reaction scenarios, for example, inside out, outside in, this type of reionization scenario. It's very different in nature. So is it good? Now we are talking about individual ionized regions and how their shapes are, etc. The largest cluster statistics is the volume only, but there are other forms which one can use to get a overall distribution of, let's say, volume of individual ionized regions as a function of volume. So that will say that, okay, if you consider a certain state of reionization, how many of these very small ionized regions are in the universe. So you can use statistics like what previously I was describing. In addition to largest cluster statistics, it will also give you information about individual ionized regions, and you can make a statistics of those. Right, so there are other approaches as well, which is, for example, this mean free path method. What it does, let's say if you have an ionized region, it will randomly select a point inside it, and it will shoot rays in random direction. And it will try to measure that ray length until it hits the boundary of that ionized region. It do this process for many, many times, and then it gets a PDF of this ray lengths. And you see that depending on how much ionization fractions or emission fractions you are considering, or different stages of your cosmic dawn or epoch of reionization, the shapes of these PDFs are very much different. For example, as you imagine that, okay, this is the emission fraction. For emission fraction of 0.4, of course, the ionized region or emission regions has become larger. So you will expect that, okay, many large ray lengths will be there. So this is more or less proxy of, let's say, typical size of your emission regions or ionized regions. This particular figure is also applicable for ionizations. So just get an idea that this is a statistics which can be used on images. Now, to have a rough idea about the length or the sizes of overall ionized and emission regions. Right, so there are also approaches like granulometry method, which use spherical filters to have an idea that if you have a complex shape, now how much of that volume is within a certain radii. If you break that particular complex shape, then how many of these spherical regions will be there? And you can make a statistics like this. The thing is, like, what it is presenting here and what I'm presenting here, these are very different. But overall, like, okay, these are independent information, and you can have some idea about, let's say, number of spherically shaped ionized regions at a certain stage of your cosmic dawn, also applicable for epoch of reionization. There is also methods like friends of friends, which basically try to connect similar type of neighbor cells and try to make statistics of individual volumes of those regions, which again give us very unique independent information. For example, these are like volume and number density of such different ionized regions. And you see that, okay, there are very large regions separated from overall distributions. So as I said, that after percolation, you will get this largest cluster, basically that region, which is connected and is a very tunnel type of very big ionized regions, and you will get like, okay, these are completely disjoint from the overall distribution of other volume of emission or absorption emission regions. Right. So there are other morphological estimators which use, let's say, concept of Betti numbers, which are, let's say, number of ionized regions or neutral regions, something like that. And the shape parameters, like if your ionized or emission region, so this is a epoch of reionization picture dominated by noise. So after you smooth, you will find a structure something like this. Now, if you just consider one particular region, for example, here, you get that, okay, there is an effective area of this particular region. This is, of course, you have to visualize in 3D, but in a 2D sense also, you will get a effective area of this region. You will get like a effective radii of this region, which is again coming from the volume. And you can also have an effective size anisotropy parameter, which, let's say, some way like, okay, if you consider this one, this is more or less a, it's not a spherical, it's a ellipsoid type of region, and you can basically have a ratio of, let's say, this axis and this axis width, and that can be used for characterizing the overall morphology of this type of epoch of reionization signal. It also has been shown that if you use these statistics, for example, the shape anisotropy parameter, effective radii, effective area of these individual ionized regions, your parameter inference will be actually much, much better if you only do that using power spectra. So I think, yeah, I have reached to the end of this discussion. So what I wanted to highlight is that now we have explored the signal and we have discussed the different physical processes of signal during epoch of reionization and cosmic dawn. During the cosmic dawn is the spin taper fluctuations, which create this emission region, positive signal, and absorption region contrast. During the epoch of deionization is mostly the ionized regions which were creating the contrast. We talked about global signal. Then we talked about that there are a set of single disk-based observation going on, which are trying to measure the global signal as a function of redshift, which is very useful. So we can also constant our parameters using the global signal. Of course, we don't have overall fluctuation informations, which are much more important because that will constrain your parameter space or understanding about the epoch of deionization cosmic dawn much better compared to when you use only the global signal, because you have the scale information there. But these are anyway independent probes. Interferometric observation, those cannot measure the mean of the signal. They only probe the fluctuations. We talked about the fluctuations in terms of various 1-point statistics, variance, skewness, kurtosis. We saw that the signal from cosmic dawn and epoch of deionization is highly non-Gaussian, highlighted by the skewness and kurtosis values. Right? We talked about 1D power spectrum, spherically average power spectrum. We saw that this is like the highly used quantity in literature, because interferometric observations are actually using that particular statistics for their measurement. We talked about a little bit that this 1D power spectrums are very much sensitive to source model, and in principle, we talked about that using low-far upper limits. So we have some understanding constants of the parameters, which we will talk in detail in the later today. We talked about other statistics like these 2D power spectrum maps, which contain much more information if we only compare about the spherically average power spectrum. We talked about higher order statistics, the bispectrum, proving non-Gaussianity. It has, of course, like a lot more information compared to the other statistics, but interpreting the bispectrum is still like challenging. So more work needed to be done. It's an active field which are probing the signal in terms of bispectrum. So you can look at the literatures. We talked about match filtering technique, which is a visibility-based technique directly from the observation, which is basically recording the visibility. You use that. Use some simply or your filter of your choice that will enhance the detectability. This can give us an indirect way of detection of this 21 centimeter signal. We talked about correlation between galaxy and 21 centimeter signal, also 21 centimeter and C2 type of cross correlation, which will give us anti-correlation. But yeah, it has benefits avoiding certain type of systematics, which is also interesting, and various studies are going on. Then we talked about image-based technique, which is, we talked about largest cluster statistics, mean free path granulometry, FOF methods. We talked about the Minkowski functionals and Betti numbers. All of these are very much useful to, again, like even an image. So overall getting the information about the morphology of the signal. So these type of techniques will be very much useful. So with that, I'll stop and I will try to see if you have any confusion. Yes.
So when you're making the binary maps, how do you decide the scale? Like, do you assign 1 to the maximum value of any pixel in the map and 0 to the?
So when you are doing a binary file, then you have to first of all choose a threshold. Given that, okay, these are the brightness temperature.
Because the morphology will change
with
your
threshold.
threshold.
Yes. So the morphology will be dependent on the threshold which we.
Is there any like standard way to choose threshold, or is it like simulation?
So each threshold will give you different information. For example, like so here, if let's say, I mean, for example, if the transition is very sharp, which is not the case of emission signal or cosmic dawn. In epoch of deionization, what you will find that transition from the positive signal to zero signal is very sharp. So they are like a threshold or yeah, playing around with the threshold. This is limited, but here, particularly during the cosmic dawn, this transition is not sharp at all. So it started from a positive value and gradually decreased to some negative value. So here the impact of this threshold is much, much more. So if you use some threshold, that will of course say that, okay, above this signal, what are the morphologies, etc. It contains a lot more information, but I don't know. So this particular thing I never checked, like if there is a way to combine every information from different threshold and get some unique information. So that part I'm not sure. Yes.
So I had a question regarding maps. So you had mentioned that maps has more information compared to either the 1D power spectrum and the 2D power spectrum, which I agree. So my question is, so how easy or hard is it to interpret this extra information? So like all the frequency correlations together, because most of the cosmological quantities are directly related to the spatial frequencies, either along the line of sight or transverse, so k perpendicular or k parallel. So if we had to like make some study about any cosmological quantities using maps, we have to restrict ourselves to smaller bandwidth so that the frequency correlation can be related to k parallel. So how I mean, is it all the extra information, is it easy to interpret?
So extra information which are basically in this diagonal term. So the off diagonal term. Diagonal term is similar to the power spectrum, this thing. Interpreting the features, for example, which are shown here, this is not easy. I mean, the people who are experts in the map type of studies, they also till now haven't interpreted what this means. Say you start with certain distribution of the signal, right? How this distribution will introduce feature which is, let's say, different if I use maps from here, it hasn't been interpreted. So till now, like even there is no study which has used these informations in a joint, let's say, likelihood or something like that in a Bayesian way to show. Need to be explored. I'm not an expert in this one, so I don't know how easy or difficult it will be. But as it is not explored, I think that okay, this is a non-trivial thing to do. Maybe like I don't know. Yes. Yes.
So one approach one can take is don't put any effort in interpreting the diagonal term. So you know there is some information, right? So and that information will be related to what Raghu was showing. So one frequency slice and the other. Now you have all that correlation, how correlated those two slides are or uncorrelated those two slides are in those off-diagonal terms. So that contains all your signal information in an abstract form. So you define a likelihood in that abstract space and then explore the parameter space accordingly. So you don't need to interpret anything. Don't try to. Yeah.
So my question is just a follow-up of what Shobhik asked. So you said that for cosmic dawn, the threshold becomes much more important because the transition is not very sharp. So in UR, for the ionization fields, it is straightforward, right? That anything above brightness temperature 0, you call it a neutral region, everything else is ionized. So how have you defined here the threshold for F heat?
So here the threshold was defined again in terms of, let's say, brightness temperature. So if you are not the main problem with the cosmic dawn signal, again, it is applicable to epoch coordination signal is that when you are considering this type of simulation and you are combining observation, then you don't have, it is mean subtracted. Each frequency channel is now mean subtracted. We actually don't have information about the mean. So from the simulation box, you know, like the emission regions, those are the emission regions which has signal value larger than 0. But when it is mean subtracted, then this is not the part. We don't know what exactly, how much as from interferometric observation, we don't have any information about the mean, so we don't know. So what we can do best is that you choose different thresholds that would be randomly chosen that, okay, You know the maximum and minimum of your distribution, and you just put different threshold. What will happen is that starting from, let's say, the maximum value and going down to the minimum value, at some point, okay, if, for example, let's say if you have few emission regions, otherwise those are far apart. And now if Lyman alpha coupling is very strong, so it will produce a signal which is very strong absorption signal, but still that signal will follow the distribution of dark matter density. So there, if you lower your threshold, then it will, at some point, it will just saturate. It will not change your statistic that much when you will basically reach to that level. So there are threshold-wise, there are some information that, okay, when it is touching the, say, base of your distribution, you can imagine that, okay, there is a base of absorption signal, and on that there are individual emission signals just popped up. In that way, like if you lower your threshold and when the base is touched, then there will be no structure actually, additional structure is forming. But yeah, I mean, if the transition of emission region is very, let's say, smooth way, then your particular statistics, this will change rapidly. If it is not sharp, it is like, okay, gradual one, it will change gradually. So what we showed in that paper is that if you try to, for example, let's say if you consider the largest cluster statistics, instead of plotting that in terms of redshift, if you just plot in terms of the fraction of emission regions, those actually are threshold independent. So it's like in a different threshold, your connections are happening in a different way. So you are choosing different threshold that will differ the population of different regions. In this case, let's say emission regions. But still, if you do your statistics in terms of the filling fraction, okay, which is like the fraction of, let's say, emission regions, your large-scale statistics will be very similar. So in a way, like the whatever like clustering or connection is happening, those are the impact of your threshold is gone away. So
you do some kind of a convergence test that, okay, beyond this threshold, if it is not changing the signal statistics much, then you stick to that threshold.
Anyway, like the threshold is not that, I mean, you can explore for different threshold. It gives you more information that, okay, what is the distributions of your signal? If your threshold, for example, like changing your threshold, if it is giving you a different distribution, means like, okay, there is a smooth transition, which is again like a additional information if you only consider, let's say, ionized region. So don't afraid to use different thresholds. This is fine. In ionized regions also, like if there is, let's say, I talked about for binary field, this is a sharp transition, but let's say that didn't happen. Somewhat a smooth transition, or let's say that happens due to resolution or something like that. There also you need to choose a threshold. That will be generally, let's say you choose 0.5 in ionization field, something like that. If you change that one, let's say 0.99, it will change slightly. You include, for example, let's say certain type of radiations which produces smooth transition. In ionized regions, this will not be as smooth as what we expect in emission or cosmic dawn type of signal. But still, like using threshold, I mean, this is fine. Like it gives you information that, okay, above this value, the sizes of signal is how much. So that is some way, like if you are changing threshold, that will say that how smooth distribution is your signal. Anything else? I think I have anyway exhausted 1.5 hours. So
let us thank Raghu again.